Back in 2017, this paper, Attention is All You Need, dropped, and it introduced the transformer. It really did change everything for AI. But that original model, that was just V1. The incredibly powerful AI we all use today was built on a whole series of clever fixes and, honestly, brilliant hacks that took that version 1 and turned it into what it is now. Okay, let's get into it. So you might be asking, why mess with a good thing, right? I mean, it was revolutionary. Well, like any groundbreaking V1, the original transformer was brilliant, but it had some problems. It was super expensive to run, kind of finicky to train, and it was missing this one key piece of information that seems so obvious to us humans: the order of the words. And that right there brings us to the first huge challenge. The heart of the transformer, this thing called self-attention, is amazing at figuring out how words relate to each other. But here's the catch. It's order blind. By default, it has no clue if a word comes first, last, or smack in the middle of a sentence. The solution then was to literally add a signal to tell the model where each word is. The best analogy is a GPS coordinate for every single token. The very first attempts did this right at the start of the process, adding a position vector to each word's data before it even got into the main network. Now, what's really cool is that the original paper actually proposed two ways of doing this. On one hand, you could have the model learn the best GPS coordinate for each position. That's super flexible, but it completely breaks if you give it a sentence that's longer than anything it's ever seen during training. On the other hand, you could use a fixed mathematical formula, this sine and cosine thing. That could handle any length you throw it at, but it's pretty rigid. So both worked, but neither was perfect. You had a trade-off. So the real light bulb moment came when researchers realized, wait a minute, why are we adding this position signal way back at the input? The place it really matters is deep inside the attention mechanism itself, right where the model is calculating which words are similar to which other words. And that was a major shift in how people thought about this problem. And that thinking led to this, the modern solution, Rotary Position Embeddings, or RoPE. It is just brilliant. Instead of adding a vector, RoPE rotates the vectors that represent each word, and the amount of rotation depends on its position. The math works out so that the final similarity score between two words just naturally depends on how far apart they are. It literally bakes the concept of relative distance right into the core calculation. And yep, this is the method most modern models are using today. Okay, so let's move to the next big challenge. Fixing the order was one thing, but the original transformer was also a computational beast. I mean, it was slow, it was expensive to run, and sometimes the training process was just unstable. The heart of this problem is something called quadratic complexity, or O of n squared. Now, in plain English, what that means is, if you double the length of your text, the amount of computation needed for attention doesn't just double, it quadruples. If you triple the length, it goes up by 9 times. You can see how as your text gets longer, the cost just explodes. It gets out of hand fast. And why does that happen? Because in that original design, every single token had to calculate its relationship with every single other token in the whole sequence. Imagine a huge grid of calculations for a long piece of text. It's massive. And frankly, most of those calculations aren't even that important. Thankfully, the fix was pretty simple and really intuitive: sliding window attention. Instead of every token looking at everything, each token just pays attention to a small, local neighborhood of words around it. Suddenly, that huge, dense computational grid becomes sparse and way, way more efficient. And you do this without losing too much performance. It was a huge win. All right, another really clever trick tackles memory usage. Originally, we had what's called multi-head attention, or MHA. Think of it like a bunch of workers on a project, and every single worker gets their own complete set of tools. It's thorough, for sure, but it uses a ton of resources. So then researchers tried multi-query attention, MQA, where all the workers had to share just one set of tools. Super efficient, but sometimes the quality of the work dropped. The modern sweet spot is grouped query attention, or GQA. This is like creating small teams of workers and each team shares a set of tools. It's the perfect balance between the speed of MQA and the quality of MHA. And finally, there's this one small but absolutely vital trick for making these giant models easier to train. When you're training something this deep, the numbers flying around inside can easily spiral out of control and cause the whole process to just fail. The original paper used a technique called layer normalization to keep everything stable. Today, most models use something called RMS Norm. It does the exact same crucial job of keeping the math in check, but it does it with a much simpler formula, making the whole training process faster and more efficient. So once researchers started solving these core problems, order, efficiency, stability, the architecture began to branch out. It started to specialize. It wasn't just one transformer anymore. It became this whole family tree of different models, each one tailored for a specific job. You can basically think of them in three main flavors. First, you've got the original encoder-decoder. This is like a professional translator. The encoder part reads and deeply understands a text in one language, and then the decoder part writes it out in another. Simple enough. Then you got encoder-only models, like BERT. These guys are like text detectives. They're not built to write new stuff, but to deeply analyze and understand existing text for its meaning and context. And finally, we have the ones everyone's talking about, decoder-only models, like the GPT family. These are pure creators, built from the ground up to just take a prompt and generate new, coherent text. So for this explainer, let's do a little deep dive on that encoder-only family. It's a perfect case study, and its most famous member is a model that really truly changed how we all approach natural language understanding, BERT. BERT stands for Bidirectional Encoder Representations from Transformers. And that word bidirectional, that's the whole secret sauce. Unlike a decoder model that reads left to right to predict the next word, BERT gets to read an entire sentence all at once. This lets it build this incredibly deep understanding of a word's context based on what comes before it and what comes after it, all at the same time. So how do you train a model to do something like that? Well, you have it play a very simple but brilliant game. You take a sentence, you randomly hide about 15% of the words, and you just ask the model, hey, predict what's in the blank. By forcing it to play this fill-in-the-blanks game billions and billions of times, BERT gets insanely good at understanding context. But here's the thing. Even a model as revolutionary as BERT was just another step on the journey. The process of tweaking, refining, and improving, it didn't stop there. Not at all. Just take a look at this. Soon after BERT came out, we got models like DistillBERT. It used a clever technique to create a version that was 60% faster while still keeping 97% of the performance. Amazing. Then came RoPE. The researchers behind it realized that one of BERT's original training games wasn't actually that helpful, so they just removed it, trained the model on way more data, and got even better results. And that really gets to the core of it, doesn't it? The transformer isn't some static blueprint that was handed down from on high in 2017. It's a living, breathing idea. It's a foundation that is constantly being challenged, refined, and improved upon by thousands of brilliant researchers all over the world. So, the crucial point is this. The amazing AI we have today wasn't born from one single dramatic breakthrough. It was built, piece by piece, on this whole series of clever fixes and hacks, RoPE, sliding window attention, RMS Norm, GQA. Each one solved a very specific problem, and in doing so, unlocked new possibilities. It really makes you wonder what seemingly small trick being worked on today is going to become the foundation for the next great leap in AI.